is I want to find this displacement at x0. All right? So do it as follows. So here's how we do. We initialize, since this is iterative, we have to initialize. We'll first start by assuming that our displacement was 0. That is, u and v are all zeros everywhere. That's great. That makes the warp really, really fast. I don't do anything. It's the original picture. Now I have to estimate the next one, d1, by figuring out what the new displacement is. That's what this new little delta d is going to be. So how do I do that? Well, I have to compute these tangents, and you can see the tangents are right there. Okay? And what I do is, based upon that tangent, come down here, it says, oh, okay, if this thing were actually a plane, this amount, that's my d hat. That's the amount I have to displace over in order to line up these points. That's assuming this thing were a plane. And if it really were a plane, that would be the amount that I would have to move. So let me do that displacement, and I end up there. So now I've got my d1, which was just d0 plus my new estimate. And guess what? I have to do it again. So now I take a look and say, I have to move this amount. So I add that to my d, and I move it that much. And guess what? I do it again. Estimate tiny little d hat this time, and voila, it turns out that f1 of x minus d3 is almost exactly f2 at this point. Okay? That's the iterative refinement. And the only thing that it takes in order to do this iterative Lucas-Canati beyond the regular one is this warping step. Given some UV that you've computed between one image and the next, take that first image, warp it through that flow field, and now you'll have almost the second image, and you just apply it over again. A couple implementation issues. In general, warping is one of those things that in principle should be really easy. In practice, you always make mistakes. I will say that MATLAB does a very fine job of allowing you to do warping in particular ways. So if you're using MATLAB or Octave, it's easy. And I think within Python, NumPy, OpenCV accomplish it as well. The other thing in order to make this work, and actually we'll get to this when we do the whole multiscale, is it's often useful to sort of take a nice bit of a low-pass filter of your images, smooth things out. Why do you want to do that? To get sort of your smoother derivatives as things work. And we'll talk more about that next time. That ends the basic discussion about Lucas-Canati. It was actually done for stereo reasons, which is kind of funny, because in stereo, you know that points have to move along the epipolar line. Whereas in motion, they can move however they happen to move. But it was originally derived in a stereo formulation. It's actually used a lot more now in the whole process of doing motion. To actually make Lucas-Canati work, you're going to have to do things hierarchically. That is, you're going to do things at a coarse scale and then get to a finer scale and a finer scale. And it's a really good example of doing multi-scale processing on images, and that's actually why we're going to do it next time. All right, welcome back to Computer Vision. And when I say back, I took a whole week off. So basically, I have no idea where we are. So hopefully you'll be more, get your act together than I do. I think last time we were talking something about the Lucas-Canati method of solving for optical flow or for motion. And if you remember, we had this problem with optical flow that we referred to as the aperture problem. The aperture problem was if you look at a little local area and you can only tell the motion that is in the direction of the gradient perpendicular to the edge. So basically, to solve that, we had to impose some form of constraints. First, we did the global constraints, then we did the local constraints of Lucas-Canati. And the idea was by having these local constraints, we could have more than one equation per pixel. And the basic idea was to pretend that all the pixels were moving in the same direction in a little local neighborhood, so we would sum up over that window. We said a 5 by 5 window, you'd have 25 equations per pixel. And that basically gave us this least squares solution, and we related that to the whole Harris corners, where we said that if the matrix here, A transpose A, if that matrix was well conditioned, meant we had two decent sized eigenvalues, it meant that the gradient occurred in various directions over that window. And we mentioned how this method of recovering how something moved was first proposed by Lucas-Canati in 1981. But critical to the whole derivation was the idea that we used this Taylor series expansion, that is, that we could approximate how something would move or how much the intensity would change by essentially fitting a planar ramp. That was the first order derivative approximation, fitting a planar ramp to a point, and then as the point would move, the intensity would change according to the slope on that ramp. But of course, there were certain assumptions built into Lucas Canati that were sometimes problematic. So the main assumption was that the pixel, as it moved, didn't change its color, didn't change its intensity. So if brightness constancy doesn't hold, then you have to do something in terms of feature detection, finding a feature from one place to another. And we've already talked about doing SIFT detection and characterization in order to do these matches. And we can combine those. In fact, we're not going to, but I'll talk at the very end about how you can combine dense estimation with SIFT estimation. The other thing we said is that possibly a bunch of points are moving one way and another points are moving another way. So in that area, within a window, you don't actually have all the points moving in the same direction. And you have to solve that with a motion segmentation. We mentioned that. We'll actually go over sort of a mechanism of doing that, not at the end of this lecture, but at the end of the next one. Oh, these aren't lectures, these are videos. So that makes them sound like they're more fun. But the most fundamental assumption of Lucas and Canati, or at least the one that in some sense is most problematic and yet fixable, is this idea that we can use that Taylor series approximation. So the idea of that Taylor series approximation is that we can make a small ramp estimate, that is a first order linear estimate, and then as things move a little bit, that'll tell us how things change. And we've gone over one method. We talked about nonlinear iterative refinement, so that if it's still the right model in terms of the point nearby is changing, but it's not linear, maybe it's quadratic or something, we use a bunch of linear successive approximations. But actually, that's not the problem that exists most often. The one that exists most often is that actually pixel motion is not small. And so you can't just assume that you can tell how things have changed by just doing a very local analysis. So to solve that, we have to do something called coarse-to-fine estimation. To illustrate what I mean, here's a simple example. So here you see on this one, on the left side, I have curves that have been shifted by only a small amount. So when I find one point value, the nearest match is actually the correct displacement. So if I actually fit a little slope through here, I can do my local estimate, and I'll eventually find the correct match. But over here, I've got a different situation. So there's one point. The nearest match will now be this red point, right? So it basically has just estimated the change to be that much, all right, where the actual shift, of course, is much, much more, all right? And so the estimated shift is too small. So the question is, how would you fix that? So let's take a look at this on a real picture. So here's an example on some real pictures. So this is 2 frames taken out of the MPEG garden sequence, and what you can see is that I've got one frame, and then in the next frame the tree moves to the left quite a bit because the camera has moved to the right. And you can see the tree in the front is including the tree in the back. Okay, so question. Do you think that this is a small enough motion to be able to run Lucas and Canati? No, look. There's a lot more than one pixel or a small number of pixel motion with a planar assumption between. I'm uncovering entire trees in the background, right? So the problem is, how could we solve this, right? How could we eliminate this problem of large pixel motion? And I'm going to show you with a single slide. You're going to look at it. You're going to go, aha, I get it. Ready? Now.
Aha, I get it.
What do you get? Okay, here's what you got. And the top left corner is the original sequence, all right? And you can see that the thing is moving a whole bunch of pixels. I don't know, maybe it's moving, let's call it 7. On the top right, you'll notice the picture is drawn the same size, but I've actually reduced the pixels in half. So now it says there's like 90 pixels across, right? Before there was something like 180. Well, gee, if I was moving 7 pixels before, now I'd only be moving 3.5 pixels. Ah. Do it again. Now I've only got 45-ish pixels, bottom left-hand corner. Now instead of moving 3.5, well, half of 3.5 is 1 3/4. Okay? That's still more than 1, isn't it? Yes. Okay? Well, cut it in half again. So now I have this picture on the bottom right. And if you look at that animation, you'll see, you can sort of see it shifting within the pixels. It's actually less than a 1-pixel motion. Okay, it's a very blurry picture, and I had to make it really blow it up, and now you can actually see each pixel in there. But you can see that the motion is a sub-pixel motion. So basically what we want to do is we want to implement a motion recovery method that takes this coarse image and then iteratively or I should say multi-scale-wise, goes to a finer and finer image. This is how it works. Right? So I've got my one image and my other image, which is why they're called image 1 and image 2. All right? And the first thing we're going to do is we're going to build what are called Gaussian pyramids. All right? And that's illustrated like this. So it's Gaussian pyramid of image 1. We'll talk more extensively in a minute about how you might go about building those pyramids. This is just notionally so you understand what's going on. So now I have these reduced pyramids. At the top level, remember I have that very blurry picture that actually only has a small number of pixels in it, and the motion between them is actually much smaller. And that's shown here, right? So here it says U is 10. So that's saying, let's suppose the shift is 10 pixels at the lowest level. Well, when I cut it in half, it becomes 5, then it becomes 2.5, then it becomes 1.25. I could keep going. So this is how I reduce the amount of motion that's present. So because I've reduced the amount of motion, I can first run Lucas and Canati between those coarsest level. And I might do the iterative thing. That's the thing we looked at last time, where I fit a plane, estimate it, shift it a little bit, estimate it, shift it a little bit, keep doing till I converge. So that will map the motion between the very reduced image 1 and the very reduced image 2, right? So I can compare that. I can find the motion between them. The question then is, what do I do next? Well, what I have to do is I have to go from the coarser to the next finer level, okay? And what's written here is warp and upsample, all right? We're going to go through the details of that, but basically the way you can think about this is I compare something at a coarse level, then I know, okay, if I were to double up this image and double up that image, I'd have to double up the motion field. I'd also have to double the amount I'm moving. We'll do that algorithm in a minute. But I could apply that to the next level, and what that will do is that will get me the next level very close to the second image at that level, and I could run Lucas and Canati again. And then I can iterate and run that over again and eventually get the entire motion field. Couple things to show you. First, let me just show you that this kind of works. All right, here's some optic flow results taken from a computer vision class, 2003, from actually a tutorial here, listed on the bottom. And you can see that when you run Lucas and Canati on that front tree without pyramids, you get sort of terrible results. And voila, when you run it with the pyramid, you get a much better result. And our goal is to be able to get that much better result. But before we can do this, we have to talk a little bit more about multiple scale. So we've been having all this multiple scale stuff. Now, this isn't going to surprise you that it relates to some of the aliasing stuff and frequency stuff that we talked about, oh God, feels like months ago. It's probably months ago. I have no idea when it was. Anyway, when we were talking about Fourier analysis and different scale. And what we're going to do now is take a little detour through multi-scale, and then we'll come back to Lucas and Canati. All right. So we talked about aliasing, and now I want to show you aliasing in terms of image subsampling, okay? So image subsampling is what? We talked about, you just throw away some number of pixels. So here we have a nice, I sure hope it's in public domain, picture by Van Gogh. This is one where you can see his ear. So on the other side, I guess there's no ear. You know about that, right? I'm going to assume you have some experience with Van Gogh. Anyway, okay, fine. So the picture on the left is an original picture where I've thrown away every sample. Maybe you can't tell. Picture in the middle, I've thrown away every other sample again, both horizontally and vertically. The picture on the right, I've done it again. Even I can tell, you probably can't tell, I can tell it's kind of looking kind of crummy. And in fact, if I blow up that picture on the right, I see this, okay? And what you're seeing here, the junk that's in here is caused by this aliasing, just like we talked about last time. And when I zoom it back up, you can see that you've brought these high frequencies in there. And there's all this stuff in here that just doesn't seem like it's the blurry version of what was in the original. And that's because it's not. It's an aliased example. So how do we handle aliasing? Well, we talked about this last time. What we have to do is we have to filter and then subsample. So what I've done now is I've taken a small Gaussian smoothing the original, subsampled, then smooth it again and subsample, then smooth it again and subsample, and now when I blow it back up, you'll notice that the Gaussian sample then, that actually looks like a blurred version of the thing on the left. Okay? And that's because I haven't done any aliasing. So to do this multi-scale stuff the right way, I have to sort of do this blurring and subsampling.
All right, let's do this in code. Write a function to downsample an image to half its size. You can do this by picking alternate rows and columns. Now write another function, this time blur and then downsample the image. Here is a test image.